is Ethan Foss. I am a PhD student in the Space Rendezvous Lab. Today I'll be presenting on my proposed work for the PhD, consisting of dynamics and control of distributed space systems in non-Keplerian regimes. So let's start off with some definitions. What is a distributed space system? So the broadest definition we can use for a distributed space system are systems of two or more spacecraft working towards a common goal. So this can consist of constellations, swarms, formation-flying spacecraft, and RPO spacecraft, each with their own levels of inter-satellite distance and navigation accuracy. In a non-Keplerian regime, basically consists of regions of space that are characterized by strong or complicated forces that break traditional notions in astrodynamics. So a lot of the new interesting regimes about the moon can contain these type of regimes. So as we see here on the right side, we see some examples of these orbits, which we'll go into further detail on. But first, let's take a look at a bridged history of distributed space systems and where we are moving towards. So obviously in the 1960s was really when we saw the foundational examples of distributed space systems with Gemini and Apollo, which did RPO about the Earth and Moon respectively and sort of laid the foundation for RPO. But it wasn't really until the 2000s that we saw the proliferation in terms of distributed space system technologies. So for example, we saw GRACE, which did planetary science about low Earth orbit. And this is really when technology developed far enough for these technologies to be demonstrated. In 2008, we had the Themis and Artemis missions, which were the first missions to do distributed space systems in a highly elliptical orbit. And they actually even did some demonstrations in a cislunar Lyapunov orbit. In 2010, we saw Tandem X and Prisma, which greatly pushed the envelope in terms of what could be achieved with formation flight. In 2011, we saw the first formation flight mission about the moon. This was Grail that did gravity field recovery, and it did these missions in low lunar orbit with large separations. And then we see a swarm mission, magnetospheric multi-scale mission, consisting of 4 spacecraft in a highly eccentric orbit. And up until now, we're seeing Proba 3. This mission has really increased the accuracy that can be achieved with formation flight missions. And concurrently, we're seeing the return to the moon with Artemis and Orion, greatly expanding our capabilities for lunar exploration. So looking into the future, we have Visors and Starry, which are both missions that Space Rendezvous Lab is working on. And in 2029, we'll see Helioswarm, which is one of the first swarms, which will be one of the first swarms to fly in what could be considered a cislunar orbit. So this mission is very exciting. And in the 2020s and 2030s, we're expecting to see a proliferation in constellations with LunaNet, which will increase communication and navigation about the moon. We had the Gateway, rest in peace, which was a space station that was to be stationed about the Earth Moon NRHO. And looking further on, we have missions like very advanced science missions like Life and LISA, which will greatly push the envelope in terms of the accuracy needed for formation flight, and the dynamical regimes that they will be situated in are very complex. So what can we take from this? Well, one conclusion we can make is that distributed space systems are expanding to new regimes. This includes cislunar, lunar, and deep space. So with that in mind, let's kind of look at some of the dynamical regimes that are interesting. So first off, we have low lunar orbit. These orbits have periods of hours and are very useful for things like geodesy, remote sensing, and staging. But they're very challenging in the sense that there are large perturbations arising from the gravitational harmonics that make motion in this regime very unstable and hard to predict. We also have elliptical lunar orbits. These are the types of orbits we would see for PNT constellations about the moon. These have periods of hours and days, and These are also very challenging due to the perturbation of Earth gravitation and also the gravitational harmonics of the Moon, which can lead to essentially collisions with the Moon if you're not careful. Moving further out, we have cislunar halo orbits. And these orbits exist in a fully multi-body regime, meaning that gravitational perturbations from the Earth and the Moon need to be considered. And these have utility for stationing and refueling, as we saw with the Gateway earlier. And then moving as far out as possible, we have orbits like the Sun-Earth Lagrange halo orbit. And these are very useful for astronomy. So the LIFE mission we were talking about earlier, this is a very useful orbit for those types of applications. And this as well is also very multi-body type regime that introduces a lot of chaos. So what are the challenges for demonstrating distributed space systems in these regimes? Well, first of all, the dynamics are quite a bit different than what we would see on Earth orbit, for example. So these dynamics can be broadly characterized as being very chaotic, sensitive, and unstable. And they have usually associated low fidelity models. But the problem is these models are typically have like a larger gap in terms of dynamic fidelity. And lastly, there are typically a lack of analytical solutions. So in Earth orbit, we can use orbital elements relatively well to characterize motion. However, a lot of times this really falls apart in these regimes. So this is a big challenge to face. And we can kind of see this in this figure here where we see basically we just take an NRHO that's in the CR3BP. If we just propagate it for 6 orbits, we see it just diverges completely from the orbit. This isn't really a property you would see in low Earth orbit, for example. Another challenge is the higher navigation uncertainty. This has to be sort of explicitly considered in a lot of control. And the last thing I'll mention is safety. So a lot of times for intense formation flight and swarming missions, we desire this notion of passive safety, which guarantees the ability of the mission to work safely. And a lot of times these notions don't exist, and so we have to confront that issue. And sort of going further in terms of prior work in this, I'll probably expand on this a little bit in a future iteration, but a lot of prior work typically works with idealized assumptions. So this includes low fidelity models, perfect state knowledge, and a lack of uncertainty. They usually consider short duration motion, which is typically quite unrealistic. And oftentimes there are little to no considerations for safety. And finally, the frameworks typically lack generalizability to various orbital regimes. So with that in mind, I'll state the contributions that I hope to answer with my PhD. So the questions we hope to answer relate to how we can improve the autonomous capabilities, limitations, and risk level of distributed space systems in non-Keplerian regimes, and how can we extend the high technology readiness levels of RPO, formation flying, and swarming techniques to the lunar, cislunar, and deep space regimes. So in this light, I propose the following contributions: new paradigms for analyzing relative motion based on dynamical systems theory techniques, adapting and developing novel guidance and control architectures, some of which I will demonstrate in this presentation. And thirdly, demonstrating the utility of these concepts for real mission concepts. So to start off with, I'm going to introduce a dynamical model known as the circular restricted three-body problem, which is usually a starting point for a lot of the analysis in multi-body systems. And in this model, we consider equations of motion as being expressed in a rotating frame. So that's something we kind of have to orient our understanding towards. And in contrast to Keplerian motion, these equations of motion only exhibit one integral of motion. And basically the consequence of this is that we don't have analytical solutions to the trajectories in these regimes. And under this model, we can actually have some very interesting behavior emerge. So in contrast to Keplerian regimes, where pretty much any state can form a periodic orbit, in these new regimes, we actually have to seek out periodic orbits, and we have to use numerical techniques to generate them. So here we see an example of some of these periodic orbits, which are have different utilities for different mission concepts. But on the left here, we have Lyapunov orbits. These were flown, for example, by the Artemis Themis mission. In the middle, we have halo orbits. So these are of significant utility to those stationing orbits that we were talking about earlier, such as the one that Gateway would inhabit. And then on the right, we have distant retrograde orbits. So in fact, some of one of the Artemis trajectories followed a distant retrograde orbit. So these are all very useful for looking into. Another aspect we're interested in is stability analysis. So say that we have some periodic orbit and we want to generate relative motion about it. How would we go about doing this? Well, the technique that we have to use leverages something called a monodromy matrix, which is essentially the state transition matrix of the dynamical system propagated for one period. And this encodes discrete stability properties of our orbit. And if we look at the eigenvalues of these periodic orbits, we notice that we have unitary eigenvalues and stable and unstable eigenvalues. And what happens is if we perturb stable eigenvalues, we can generate these things called stable invariant manifolds. And for unstable eigenvalues, we can generate unstable invariant manifolds. So these basically characterize regions of the phase space in which you can emanate or emerge from a periodic orbit. But what happens if we perturb these unitary eigenvalues? So what happens if, when we perturb these unitary eigenvalues, is we actually generate something called a quasi-periodic torus. And basically, this is a higher level notion of a periodic orbit. So in dynamical systems, you can think of equilibrium points being zero-dimensional equilibria. You can think of a periodic orbit as being a one-dimensional equilibria. But actually, you can extend that further. And in fact, this is what we see. We see quasi-periodic tori emerging from these periodic orbits, which characterize two-dimensional equilibria. And just to sort of outline what this means theoretically, basically what this consists of is a diffeomorphic mapping between tori frequencies or angles along the torus to positions and velocities in the phase space. So with that in mind, let's sort of outline why this is useful or even necessary to consider in the first place. Well, if we look at the Keplerian regime as an analog, what we see is that neighboring absolute motions form relative motions if we look at it from the perspective of the spacecraft on a periodic orbit. However, in cislunar regimes, the perspective has to be shifted a little bit. Instead of neighboring periodic orbits forming relative motion, it's actually neighboring quasi-periodic tori that form that relative motion. So with that in mind, let's see how these ideas kind of extend to the high-fidelity setting. So in that sense, I'm just going to quickly introduce how we characterize absolute motion in these high-fidelity models. Basically, what this consists of are n-body dynamical models, including sun, Earth, and Moon gravitational forces, and these forces are generated from like an ephemeris. And in terms of relative motion, basically an easy way to sort of study relative motion in these high fidelity settings is to look at the state transition matrix, which simply characterizes how initial states at some initial time transform to some state perturbation at a final time. The last thing I'll mention is that we often consider relative motion in like a velocity normal binormal frame. So that's something we have to orient our perspective towards. So with this in mind, let's outline some of the challenges involved in demonstrating distributed space missions in an ephemeris setting, which is what a spacecraft would ultimately fly in. A key thing to note here is that ephemeris models do not admit periodic solutions. So what we see is we actually have to perform this non-trivial process of generating some trajectory in a nearby vicinity to these periodic orbits using differential corrections. And the key thing to note here is that we ultimately break periodicity of our orbit. So in a lot of ways, this makes it challenging to apply a lot of the techniques that leverage periodicity of orbits to these settings. The other challenges arise from the fact that, one, we need to do absolute control with respect to this orbit. As I mentioned earlier, a lot of these regimes are completely unstable as opposed to only parabolically unstable. And basically what this means is that you will exponentially diverge from these trajectories over time. So it's not as simple as we can just perform relative motion control, we also have to perform absolute motion control. The other challenges are we need to consider navigational error and the fact that spacecraft can experience propulsion cutouts. And basically what this means is that you can have, if you are not careful in how you design your guidance and control system, you can end up evaporating the formation essentially. So with this in mind, I'll present some results that I presented at the Astrodynamics Specialist Conference last year, in which we proposed and demonstrated a novel guidance and control solution for long duration station keeping of cislunar formations and swarms. And basically what our results consist of, we consider realistic conditions. So that means we simulate in high fidelity environments with navigation errors and missed thrust events. And we also perform this on this long duration formation keeping as opposed to very short instances. We also introduce a novel technique for efficient handling of passive safety. And we show that this guidance and control framework is modular and highly scalable to many agents. So one key question we have to answer for generating relative motion is, can we still generate this motion in about a high fidelity reference trajectory, even though they are non-periodic? And the answer here is sort of. Basically, you can propagate the state transition matrix forward for integer periods, and we still see that the eigensystem admits this familiar eigenstructure, but it's slightly perturbed. And in that sense, we can still generate these reference orbits, with the caveat being that they don't exist indefinitely. And so basically what we have to do is implement some strategy where we stack together a sequence of relative motion trajectories. And in terms of our architecture, basically we can leverage these reference trajectories that we generate into a control architecture which completely decouples absolute and relative orbit control. And basically the way we achieve this is by converting the states of the formation into an absolute and relative state, and simply summing together the control that is outputted in an absolute and relative sense. A really important aspect of our architecture is the introduction of a control barrier function. And basically this ensures that we can decentralize the absolute and relative control law without introducing any aspects of unsafety to our system. So we can explicitly enforce that the spacecraft maintain a safe separation over time in a way that is computationally efficient. The last thing I'll mention is that we need to be a little careful about how we consider the maneuver timing for the NRHO. So this might be a little bit confusing for someone who's familiar with Keplerian motion and how you would control an absolute orbit in that sense. The difference here with NRHO is that we often perform the orbital corrections at apolune as opposed to perilune. The main reason for that is just because navigation errors are usually significantly larger at perilune, and that sort of mandates that we have to do these maneuvers at apolune in order to make sure we aren't incorrectly maneuvering our system. And with that, here is the absolute station keeping control strategy that we use. It's basically a nonlinear model predictive control strategy. It's not significantly different than what you would see in current literature. And in terms of our relative station keeping control, we simply use a two-impulse relative targeting law. And basically what we see is that these two on their own will be sufficient for long duration formation keeping. And the last thing I'll mention is the introduction of the control barrier function. I won't go too much into the details here, but under various assumptions, we can enforce stochastic keep-out zones. So that means we ensure safety to some probability margin. And we can essentially endow the system with this notion of what I call recursive passive safety. So basically, under the feedback law that we introduce, if we couple this feedback law with our control barrier function, then we can ensure that the system will never have these these close encounters of the spacecraft, which is obviously really important from a safety perspective, as we were mentioning earlier. So to show these results, I'll basically briefly set up our simulation protocol. Basically, we consider realistic navigation and control conditions. The dynamics are simulated in a high-fidelity model, and we demonstrate this under various test scenarios at various separations and various agent count. And we do this over, I think, around 50 years of cumulative simulation time. So to sort of visualize these results, I have these animations that show the absolute motion that the formations undergo and the corresponding relative motions that the spacecraft form with respect to each other. And basically what we'll see is that we maintain bounded absolute motion with respect to the reference trajectory that we see. And we see on the bottom plots the relative motion of the spacecraft with respect to each other, or with respect to a virtual chief. And we see these follow pretty well the reference relative motion solutions that we assign to them. And we'll also see in the maneuver profiles we have various instances of missed maneuver events, or basically periods of time where spacecraft randomly miss a maneuver. And despite this fact, the formation is able to maintain safety over time and bounded relative motion. Lastly, we have a 5-agent scenario here, and the last thing I would like to note is the addition of the control barrier function. And what we see in this example here is that if we do not consider the addition of control barrier function, we will encounter these unsafe events. So on the top figure, we see that under the same simulation framework, without the addition of a control barrier function, we have this instance where following a mismaneuver event, two spacecraft come to within 30 meters of each other, which is obviously very not ideal. However, if we activate our control barrier function, we see that the control barrier function cleans up these unsafe events. And with the addition, we see that the spacecraft maintain a safe separation for the full duration of time. And lastly, I'll just note that the total delta V expenditure for this scheme is very modest. It's around 2 meters per second of yearly expenditure, which is consistent with what we see for absolute station keeping. The algorithms are very robust. They converge in all trials. And the computational efficiency of these algorithms are very low. And we didn't encounter any unsafe or unsuccessful trials over the 53 cumulative years of simulation. So with that in mind, I'd like to move towards the future work that we are considering. And basically, the main idea here is how do we move to the more general setting? And with that, I propose 3 avenues in which we will do this. So the first one consists of the relative motion dynamics. And in this light, we would like to propose the introduction of a new relative motion coordinate system that leverages Kolmogorov-Arnold-Moser theory. And as we will discuss, we have the possibility to increase the linear validity of these coordinates over the state space. Secondly, we would like to consider improved control schemes. Obviously, these regimes consist of harsh environments in which we need algorithmic robustness and reliability. So that's something we would like to move towards. And we'd also like to add explicit considerations for uncertainty and control. And then lastly, I would like to demonstrate these new techniques in relevant mission demonstrations. And I'll talk about the specific missions I have in mind. So firstly, let's talk about relative motion dynamics. To sort of motivate this work, let's consider the Keplerian regime. So suppose we are in a periodic orbit about the Earth. There are sort of 2 different paradigms for considering relative motion in these regimes. So obviously we have the Hill-Clohessy-Wiltshire equations. The main issue with these equations is that their region of linear validity is very small, as we know. However, if we use relative orbital elements, we know that the region of linear validity expands significantly. So basically what that means is motions that are at completely different sides of the Earth can be embedded in a coordinate system in which their motion involves linearly. This is something we know about relative orbital elements. The idea here is maybe we could extend this idea to a more general system. And with that, we propose the introduction of something called relative action angle variables. So action angle variables are essentially the most general notion of orbital elements that we have for general regimes. And basically what we see is that if we leverage these coordinate systems, we can expand the region of linear validity of these coordinates to encompass a much larger region of the phase space. So this is obviously significantly more useful. Basically, in the results I showed earlier, we were leveraging only the first option. But if we wanted to generalize further to larger separations, then the second option will be obviously much more preferable. The other interesting thing about these variables is that they intrinsically encode equilibrium conditions. They're valid for general cam tori, so that means we don't need a periodic orbit per se. We can introduce these variables for general cam torus, and they are unique and independent of coordinate frame. In terms of control, the three things that sort of separate non-Keplerian regimes from the Keplerian regimes are the need for greater enhanced algorithmic robustness, considerations of uncertainty, and considerations of absolute orbit control. So the extensions we propose in my PhD would include enhancing state and input constraint formulations in a way that maintain input sparsity. So we've already taken several actions in this light. So these are some results that I'll be presenting at the American Control Conference later this month. But basically what we show is that there are different formulations for input and state constraints that can maintain sparsity of the control input. And so this is sort of a theoretical insight that has been overlooked so far. And the last thing I'll mention is we would like to extend these ideas to the impulsive distribution steering setting. Instead of just commanding an initial or final state, we want to command an initial and final distribution. So in this slide, we've made some theoretical connections to optimal transport that we hope to seek further. And then the last thing I'll mention is the idea of extending these techniques to relevant mission demonstrations. So in this slide, I'd like to bring up the LIFE mission, Large Interferometer for Exoplanet Detection, and the STARry mission, Starlight Acquisition and Reflection Towards Interferometry. And the really interesting thing here is that as part of the PhD, I've been fortunate to work on the STARry mission. And the STARry mission itself is a technology demonstrator for the LIFE mission, which plans to inhabit a Sun-Earth Lagrange point orbit. And so basically what that means is a lot of these techniques for doing formation flight need to naturally extend to these new regimes. So this opens up a really interesting avenue for the PhD in terms of extending these theoretical insights to a practical mission demonstration. So yeah, I think that's pretty much it. So yeah, I'd just like to conclude by noting the contributions that I've worked on so far. So I've demonstrated a guidance and control architecture for formation flight applied to high-fidelity cislunar regimes. And one key aspect of this formulation was a novel technique for enforcing passive safety in cislunar space. I've also worked on impulsive optimal control in terms of expanding the constraint formulations that we have access to. And I worked on mission and control design for the STARry mission. In terms of next steps, I would like to develop a framework for local action angle variables about high-fidelity reference trajectories, expand impulsive optimal control techniques to sparse state constraints and distribution steering, and develop flight software for STARry and extend these concepts to the LIFE mission. And with that, I'll take any questions. Thank you, guys.